Нет, Гоша, вы торопитесь.
По-русски или по-английски?
По-английски, по-английски.
Ага. Так, это нужно вот так, по-идеалу. Главное, чтобы это не свалилось. Так, это нужно с собой.
Все, поехали.
Так. So, I'll begin with recalling the classical Toda system, and then passing from it to generalizations, which are, there are numerous generalizations of Toda systems, but there are two full Toda systems. One is constant Toda system, full constant Toda system, and the other one is a full symmetric Toda. I'll speak about symmetric first of all, but I'll mention both. So classical Toda system is classically defined as the following Hamilton equation. Suppose you have n points on a straight line with coordinates q1 to qn, and momenta p1 to pn. The Poisson structure is standard one. That is to say, the only non-trivial commutation relation is given by the equation that commutator of pi and qj is equal to delta ij up to all the other trivial zeros. And the Hamilton function of the system is given by the sum of its kinetic term pi squared divided by 2mi, but okay, actually we can remove this m for good from our notation. It doesn't change anything. Plus the potential term, which is a bit strange. It is exponential. Sum of the exponents of the differences of qi minus qi plus 1. Here, indices correspond to the numbers of the points, but it doesn't mean that the points are ordered in accordance with their coordinates. That is to say, some points can be, the order of the indices need not coincide with the order of the points on the straight line at all. So this system has been studied, it appeared, as the story goes, it first appeared in 1950s in the famous Fermi, Ulam, I think Fermi, Ulam, and there's a third, Pasta. Fermi, Pasta, Ulam, and there's nowadays they also add some women's name to this list. It was the lady responsible for the programming of this computer. So they had an kind of numerical experiment to check the properties of various Hamiltonians, and they observed that this Hamiltonian corresponds to a system which behaves pretty regularly, which implies that it is integrable. This same system reemerged a few years later, well, about a decade later, in a paper by a Japanese physicist, Morizuki Toda, I think. Morizuki is his name, and Toda is family name. And so the interest to this system was revived by this paper, and ever since that time, these systems and this system and its derivatives, its generalizations, are called Toda systems. So this in particular is called Toda chain or open Toda chain sometimes. A few years later, after Toda, it was proved finally that this system is in fact integrable, And the easiest way to do this, integrability, to prove the integrability in Liouville sense. Is to introduce new variables. I hope, yeah, I believe it is like this. Yeah, it is. So now we take AI to be equal to EI divided by square root of 2. QI equal, sorry, BI equal to the exponent of QI minus QI plus 1 divided by 2. I goes from 1 to n minus 1 now. And I believe there was some constant coefficient here, which I don't remember. Moreover, I must say that in a well-known paper, which by Yuji Kodama and somebody else, which was denoted 50 years jubilee of Toda system, published about.
So what is in front of
some coefficient.
Coefficient.
Some coefficient, which I don't remember. This coefficient was not correctly set in that jubilee paper. We can check it. It doesn't work, at least. Maybe they, at least in the version of the paper which was available at the time in the archive, it was not correct, as far as I can remember. In any case, after this change of variables, this commutation relation takes a very more interesting form. So again, BI commute with each other, AI commute with each other, and the only non-trivial commutation relation is between AI and BJ. And it's again something like delta I J B with some coefficient, which I don't remember. B I maybe minus delta I J minus 1 B sorry BJ, and here we have yeah, something. I think it's something like this. Yeah, I'm sorry for this. It's not very hard to restore from this equation, but you just commute and use the fact that the differential of exponent is equal to itself, and so it's easy. Right, easy exercise, which I don't want to perform. In any case, we have this kind of commutation relation. And using this commutation relation, and using also the fact that this Hamiltonian function can be rewritten in the form AI squared plus BJ squared. So this is probably 1, but yeah, I don't remember. Yeah. We see that the equation, the Hamilton equation, takes the form which can be written in, it takes the following Lex form. It introduced the Lex matrix. We have A I on diagonal, B I off diagonal, and below the diagonal as well. So both diagonals are taken by BJ's and zeros elsewhere. Then the Lex equation is given by the following trick. You anti-symmetrize the matrix L in naive way, and just delete the diagonal, preserve the signs in front of be above the diagonal,
Never mind.
change the signs below the diagonal, right, preserve zeros, and then the Lex equation will look like L dot is equal to the commutator of ML and L up to the sign which you can restore here. Now it is easy to, now it is obvious that the function, the invariant functions of the matrix, Lex matrix L are first integrals of the system, and it is also easy to see that they're all in involution. For instance, you can take the functions given by traces of L to the power k for k from 2 to n. As far as the first trace of L itself is concerned, it is not just a first integral, it's actually a Casimir function. So in this case, you can actually set the trace to some constant. For instance, you can set it equal to 0. And that actually proves the integrability of the system, of the Toda chain. Now, to look at looking at the Lex form of this equation is probably the easiest way to generalize the Toda system. Namely, you actually keep or modify somehow the first term. There's antisymmetrization or some projector applied to the matrix L, projector, linear projector applied to M, to L, and then you look for all shapes which you can give to the matrix L such that the commutator of L with a certain projector of L will have the same shape. For instance, you can add to this three-diagonal form, symmetric form, you can add something here and here. And in this way, you get a system called the closed Toda chain, which you can actually interpret as the antipole of points on a circle, which interact in the same way as before by
You mean you take this Lex equation and
Yeah.
modify?
Yeah, modify the shape of the matrix. And also I can a little bit modify the projector.
And you again obtain the integrable system.
Not necessarily, and that actually gives you some Lex forms, and you can investigate if some of these Lex forms correspond to integrable systems or not. So far, I think all known, all studied systems of this sort are very integrable, as far as I know. But I don't think that all possible variants have been studied in this way. I think, well, a few years ago, I refereed a diploma paper by a student of Anton Eisenberg, and her task was to find all possible shapes of matrices for which the usual projector to antisymmetric matrices preserves this equation. She gave quite a large list. I think that all such matrices were parameterized by certain graphs, certain properties, and it's interesting to see if some properties of graphs are needed for this system to be integrable or not. But I don't think this has ever been studied. So there are two important systems which are obtained in a very much the same way. The first is full constant Toda system. custom Toda. Well, I'm not quite qualified to speak about it. As far as I can remember, the matrix shape is pretty peculiar. You have lower triangular matrix, and then above diagonal you have ones, and zeros above, well, in top, all the rest. And then you need to modify the projector, of course. Here you need to take the projector to, I think it's projected to lower triangular. So instead of taking M, you take the projector to maybe to upper triangular. Upper triangular. No, it's upper triangular. To upper triangular. And this gives you a pretty nice system. And it turns out to be integrable as well. Well, this far as this is concerned, I'm not sure. I'm sorry for this, because it's not the subject of my talk. But another generalization is the full Toda system, which I'm going to talk about. It is the full symmetric, and it's the most naive thing you can come up with. So you just take L to be arbitrary symmetric matrix. Oh, sorry, one. So you have arbitrary symmetric matrix. And then you take M of to be naive symmetrization. That is, you delete the diagonal again, you preserve the sign of the elements above the diagonal, and you change the signs of the elements below the diagonal. And now, since the commutator of anti-symmetric matrix and symmetric matrix is symmetric, which is a very simple thing to check, you can write down the equation as before. And again, it turns out that, of course, all traces of L to the power k, k times 2, and are in fact first integrals of this system, functionally independent first integrals. But now they are not nearly sufficient to provide the integrability of our system, because now the dimension of the phase space is proportional to n squared divided by 2. And we have no more than, well, n minus 1 first integrals of this sort, even if we don't care about the calendars. So I'm going to talk about this system and about its properties. This talk is based on a series of papers joined with Georgy Sharygin, Dima Tavalaev, and Alexander Sorin. So various papers, had different, different combinations of these 4 authors. So I just gave all the names. Yeah. Actually, it was Alexander Sorin who introduced me to this problem. He was, studying this system together with Yuri Chernikov. But then Yuri asked me some questions about the properties of Lie groups and Lie algebras. Now, gradually, I got involved into this topic. So first of all, I need to speak about some facts which are not proved by us. So now the main part of my talk will be related to this full symmetric Toda system. I'll speak about its properties. I begin with explanation why this system is in fact Hamilton system. I'll also say a few words about its additional first integrals, which are not ours. These facts were not proved by us. These have been known. But after this, I'll move forward and speak about the properties of its trajectories and about the properties of trajectories of its generalizations. And further speak about its integrability in the sense of Libyansky theorem. It turns out that this system is not just Liouville integrable, it's also Libyansky integrable.
You mean in
it means
quadrature?
Yes, I mean, well, according to the Libyansky theorem, to which you introduced me a year or two ago, if you want to have integrability in quadratures of a system, of a differential equation, it is sufficient to have the Lie algebra of symmetries of this differential equation such that this Lie algebra is, first of all, sufficiently large. That is to say, its dimension should be equal to the dimension of the manifold minus 1, more or less. First, and second, well, it should act freely, locally, at least locally freely on the manifold. That's also evident, but also this Lie algebra should be resolvable. So I'm going to construct such Lie algebra in this case. Okay. So this is not yet published, by the way. Okay. So first of all, why the system is in fact a Hamilton system? First of all, I need to introduce the Poisson structure. Poisson structure on the space of symmetric matrices. On real symmetric matrices. Let's be real. Yeah, I forgot to say that for me, all these systems are for real matrices, not for complex matrices. Well, there are a few ways to do it. I begin with something very stupid. I identify symmetric matrices with the space of upper triangular matrices, which I actually dualize somehow. And then I use the standard Poisson structure on this space. Yeah, you can do this just in a very naive way. You can say that when you have an element B in B plus, you just take a symmetric matrix L, and then the pairing between these two are given just by taking Bij and times Lij, and that's all. This is the pairing. Just this. Well, some coefficients might be necessary, something like that. So this actually is nothing else but the Killing form. Killing form on the SLN, where both Bm plus and symmetric matrices and seat, right? Both the seat. And this pairing, when you restrict this pairing to these two subspaces, it's non-degenerate, so you can identify, and dimensions are the same. So just identify one with the other using this synchronization, using this pairing. That's all. A more refined way is to consider the so-called, I think it's I think it's what they call QR decomposition of Lie algebra. Decomposition of Lie algebra. So n is equal to B plus n plus SON. And then you use the killing form here. And killing form.
What does it mean, QR?
Oh, Q is up. I think it's what they call QR decomposition. It's usually done for matrices. When you have a matrix, you decompose it into the product of a triangular matrix.
Oh, this abbreviation.
Yeah, I don't remember. Actually, I don't remember. It's very standard.
It is something in numerical analysis.
In numerical analysis, they use it very often. It's it's a very fast way to diagonalize a matrix, to find its eigenvalues. And that's actually related to Toda system, by the way. The fact that numerical analysis gives you, it's just this. Yeah. I think it comes from numerical analysis and from the fact that when they use this decomposition, every metric is a product of upper triangle.
But decomposition is a form of special real form of SLNC.
Well, I only work with real matrices. In fact, this is kind of real part. You can call it a real part of some Iwasawa decomposition or something like
part of Iwasawa.
Yeah, something like that. But actually, it's very, very long story, and I'll barely touch it today, I think. Okay, so you have this decomposition, and you let symmetric matrices actually have another decomposition, which is called the Cartan decomposition. SON plus symmetric. Now, this decomposition is orthogonal with respect to the killing form, and that actually means that when you go to pass to the duals, this will be identified with this, with dual to this, and that actually allows you to pull the Poisson structure from this dual space of a Lie algebra to the space of symmetric matrices, which otherwise do not have such structure. You can write down the Poisson bracket of two functions, smooth functions on symmetric matrices. Using the following formula, you take L and pair it with the projectors onto upper triangulars of F, of differential of F at L, differential of G at L, and actually, yeah, commutator. So this is just the restriction of the standard Lie Poisson bracket to the subalgebra, and you can actually rewrite it in terms of the projector M. This projector M from symmetric matrices onto SON turns out to be nothing else but the restriction of a natural projection from SLN onto SON with respect to this direct sum decomposition. Right. So you can now rewrite it in terms of M using the following property. So here I use the differential of F as function on symmetric matrices. So its differential is a symmetric matrix in some sense, right? Its differential in some sense is symmetric matrix. So you have following up to the sign of the following formula. I think it's minus rather than that. So here you have it. So this is actually the Poisson bracket, and now it is. You can use this formula to prove that traces of f to the power k are in fact involutive, right? And in fact, h, the Hamilton function, should be equal to the trace of L squared as before, well, maybe 1/2 of that. So that's actually the explanation why the system is Hamilton. Now let me say a few words about why it is integrable. Even though now I have an explanation, I have given you the explanation why the system is Hamilton, it is still far from being clear why this system is in fact integrable. We still have much less first integrals in involution than we need. So we need additional first integrals, and these additional first integrals are given by the so-called chopping procedure. Due to Beicht, Lee, Nando, and Tomei. So it looks as follows. You take the L matrix, the Lex matrix, so it's symmetric, so I don't care what to write here. A and N. Then you subtract the scalar matrix lambda times the identity, right? So we get something like that. But after this, you do something unexpected. You delete the first k rows and the last k columns. What you obtain will be a matrix depending on the parameter lambda, but now this parameter will stay off diagonal, off the main diagonal. So when you do it k times, you denote this something like that. And then you take determinant. So this determinant is a polynomial. Of degree n minus 2k. Of certain coefficients which depend on the matrix L and lambda goes to the power I. And it turns out that the ratios of such of these coefficients, I of L divided, for instance, by I0 of L, they are in fact first integrals in involution of this system, and they are functionally independent. We prove that these first integrals in involution are in fact, well, first integrals in involution. I don't know the way it was proved in the original paper. In the original paper, well, looks pretty cumbersome to me. I believe it's been done as a combination of certain computations, pretty straightforward. Maybe not very hard. I was told they are not hard, like people who read them thoroughly. And the idea due to team that you can project your elements to subalgebras. So there is a filtration of subalgebras.
The number of these first integrals
is
exactly
proportional.
what we need, yes?
Yes, it's proportional to n squared a by 2. But there are certainly some Casimir functions. So if you take into consideration all Casimirs, you get the integrability. You get integrability, right? Yeah. So the fact that they commute is not as simple as it might, well, one probably would expect, but it's not very hard. It's actually, for me, the proof that I know, the proof that I came up with at the moment, is the following. Let me sketch this proof. It's quite interesting, in my opinion, in itself. Proof. Well, first of all, let me recall the famous add the custom seams construction. Add the custom seams. Custom seams. I think it's with Y, not with I. Maybe E somewhere. I don't remember how it is spelled. I think it's science, something like that. It goes as follows. Suppose you have direct sum decomposition, a Lie algebra, if you write, well, which has a direct sum decomposition into two subalgebras, G0 plus G1. We don't ask these subalgebras to be ideals in the algebra sense, but they are, well, just subalgebras. Then you take the corresponding decomposition of the symmetric algebra of G as the symmetric algebra of G0 plus G0, sorry, plus G1 as G, right? And this direct sum decomposition. Suppose now you have two functions, f and g, which commute with each other. They are elements in Sg. And also they, I think they should be.
What is the structure? What does this theory?
They Poisson commute in the sense of Lie Poisson bracket.
Okay.
Yeah, just Lie Poisson bracket. Then you assume that yeah, that they are G0 invariant. I think. I hope I'm not making a mistake. G0 invariant. Yeah, I think so.
This is an assumption
Yeah.
on this.
Yes. So they both of them are G0 invariant, and they Poisson commute. No. This is assumption for F and G. For F and G. So, maybe G1 is there. I'm not sure about this. I don't remember. We are going to restore it right now. So you write down F and G, equal to 0, right? So you get f as the sum of element here and here. F oh, G, sorry. G0 is plus G1. Yeah, also observe that when you have two elements from here, so these are Poisson subalgebras. This is Poisson subalgebra. This is Poisson subalgebra. Right? These are Poisson subalgebras. So now I write down these. Yeah. Oh, sorry. I'll probably begin with, yeah, F0, G0. F minus F1, G minus G1, right? Okay. Now you continue like this. This is equal to Fg. Plus F G. Oh, I think it's better like this. Sorry. Minus G0. Yeah, now it's better. Now I'm sure. Yeah. So I'm sorry for this. It is. I think it's well known, but I think it's worth to do it for the sake of completeness. G0 minus minus
0G.
F0G, and finally plus F0 G0. Okay. Now this is 0 because of the assumption. This element actually belongs to SG0, and we assume that F were G0 invariant. F was G0 invariant, and therefore this commutator is equal to 0. Same here, right? So we have F1 G1 is equal to F0 G0, but they belong to the complement direct in this complement direct summons. So they must all both be 0. That's a very simple, as you see, construction. That's very efficient. It allows you to construct commutative families from invariant commutative families on larger space. So you now apply it to the following situation. You take the matrix, you take X to be any matrix from SLN, right? And you take the standard characteristic polynomial of X, right? And now you differentiate. So this gives you the coefficients of these polynomials. Of this polynomial are just, as you know, they're just central elements. Poisson center of SLN. Now you consider SLN as the composition of B plus say SON. Oh, you can actually take N minus. I don't even care about this. N minus. There is some decomposition, right? Now, so it is you can now do the following trick. Sorry. Follow the better trick SON. You want to, so you identify this with symmetric matrices as we have done before, right? So we want to obtain, so we use this trick to obtain this family from invariant functions on commutative family functions on SLN. You take coefficients of this polynomial, they're central, and therefore they verify these two conditions. But then you do the following thing: you differentiate it by this top right element in your matrix. Then you differentiate it by the second element in this row, 2 x2 and minus 1, and so on. Differentiate the coefficients. So what you will receive will be commutative family. When you differentiate, differentiate once, differentiate twice, however many times you do it, you will still get a commutative family which follows from the argument shift method, nothing else. So argument shift method claims that what you get will be commutative family, always. That's the first step. So that's the first thing we have. Now, as for the B0 invariance, B plus invariance, they are not invariant, but they're semi-invariant. And it follows from the fact that the coefficients are invariant, but these differential operators, they are not invariants, but they are semi-invariants. Therefore, however, when we differentiate it several times, we'll get semi-invariants with the same, which correspond to the same character of B plus. So when we take ratios of two such semi-invariants, we get invariants, and that's precisely the chopping procedure. That's how I, explain this to to myself. Okay, so let's go on. That's the chopping procedure. Now let us speak a little bit about the trajectories of the full symmetric Toda system. Trajectories. So let me do the following thing. L is symmetric, real symmetric matrix, so I can always decompose it into the I can always diagonalize it with the half of symmetric matrix. So lambda is the diagonal matrix of eigenvalues, and psi is an element in SON. Right? Then we can rewrite the Toda system in terms of psi. Well, if you're familiar with this technique, I think it's sometimes called the beta Ahier's or something like that function of the system. But for me, the true explanation of this is the following. Consider the vector field on SON, which is obtained by the following construction. I will denote this vector field by T lambda of psi, and it will be equal to the following thing. I take minus maybe m of psi lambda psi transposed, right, and multiply by psi. So this is a vector field. So this is an antisymmetric matrix. This is an element in the Lie algebra SON of the Lie group SON capital.
What is M?
Sorry?
What is
M is this standard projection. The same projection we used before.
Mhm.
So we have this projection, it gives us an anti-symmetric matrix, so we interpret it as an element in SON small in the algebra. And I use the right translation in the Lie group to obtain a vector field on the Lie group, SON. Right? Then the following is the reason why this vector field is almost as good as the original Toda system. This one. So here's what we do. Let psi of t be a solution of the equation psi dot equal to t lambda psi, right? Such that psi of 0 is equal to psi 0, such that psi 0 lambda psi 0 transpose is equal to L0, some symmetric matrix. Then sorry, then L of t equal to psi of t lambda psi of t transposed is the solution of the Toda system, of Toda equation such that L of 0 is equal to L0. And it's very easy to check. You just differentiate this equality and use the definition of our vector field, nothing else. So it's just straightforward. And that's why I will always call this vector field the Toda field. And you can, you can study either the Toda system or the Toda field and get more or less the same results. You can always reinterpret the results you obtain about Toda field in terms of Toda system and vice versa. Although sometimes it can be a little bit tricky. So,
not any solution of the Toda can be
well,
in this.
it's always,
I
of course,
just asked.
and always, of course,
Are presented in this
of course. It's very easy just to take this Toda system, take the trajectory, then you take its, well, how do you call this, the initial point, you diagonalize it, it's always possible. Sometimes it's not always unique, that's the only problem. But then in that case, you can choose either. You can choose any solution of this diagonalization problem. You diagonalize it, you take the trajectory of this Toda field through this point, which always exists by the ordinary differential equations theory, and then you plug in and you check that you get the solution, and since the solution is unique, you obtain the solution you want. Okay, so you get, so I'm going to study this Toda field, and there are a few facts about it. So first of all, this vector field is in fact gradient. Is a gradient field. It's already quite interesting because this gradient field governs the behavior of a Hamilton system. And the properties of gradient fields and Hamilton fields are sometimes opposite. For instance, gradient fields cannot have closed trajectories at all, because they always go in the direction of the growth of the gradient of the function. On the other hand, the Hamilton systems should preserve certain, measure. And gradient fields cannot preserve measure because they go to where they always their limits are always some points, right? But it turns out that here everything goes nice, and the reason for this is that the measure which you have on the Hamilton side of the story is singular. So the fact that it is not preserved is not very surprising. And moreover, all the trajectories of this Hamilton system are also, are not closed as well. You can always check it. Now the singular points of T lambda are well, up to science, permutation matrices. Permutation matrices. And this corresponds to the fact that the stable points of the Toda system are given by diagonal matrices on Toda side. I will assume that these eigenvalues are distinct from now on. It follows from the gradient properties and this observation that the trajectories of T lambda go from one permutation to another always. Well, I mean, the trajectories go from one permutation to another as the time goes from minus infinity to plus infinity. And the first result, which is due to our group, is that we identified what points, what permutations can be connected by a trajectory of Toda field. And the claim is as follows. There is a trajectory. There is a trajectory of Toda system that connects two permutations. You can think about this as permutations of the eigenvalues. For instance, you can think that all the eigenvalues are ordered, they're all distinct, they're ordered in the in the direction of their growth. Well, they're the initial ordering is the natural one. And then you can consider any two permutations, and they can be connected by a trajectory if and only these permutations are comparable in the sense of Brouwer order.
In the sense?
Of Brouwer order of permutations. Comparable by Brouwer order. The strong Brouwer order.
Oh, please explain what is
Brouwer order. Well, I think it is probably so in this case, it's, I think it's probably better to give the let me think. So Bra order is given by the following.
This is the order on the symmetric.
Yeah, the order on symmetric groups.
Yeah.
I just don't remember the details. I know how to do this in Coxeter groups. And of course, since symmetric group is a Coxeter group, you can rephrase it in terms of symmetric group as well. But I prefer to speak, probably give a more down to the earth definition. I try to remember it with our order. No, it doesn't take much time on SN. So you have two permutations. U, which is U1, UN, right? And W, which is W1, WN. So suppose, I think it is as follows. If we can, if we say that U is elementary while preceding W, if if there exists, if U is equal to some transposition composed with W, I think on the left. In this sense, I mean, the transposition of two elements. And the number of, so not every transposition is this, but you should also assume that the number of inversions, probably vice versa, number of inversions in U plus 1 is equal to the number of inversions in W. I think it is this, as far as I can remember, this elementary. You can actually rephrase it in terms of Coxeter generators. In Coxeter generators, you need to choose a minimal word that represents W and minimal word which represents U. And then you need to assume that the minimal word for U lies inside the minimal word of W, something like that. Yeah, but it is actually quite complicated. I mean, yeah, just compositions of this. It's probably easier to So for instance, in case of S3, you have the following diagram of this order. Have the initial, then you change the order of 1 and 2, I think, right, of 2 and 3. Then you can change the order of 3 and 1. 2, 1, 3. Oh, sorry, 2, 3, 1. And here you can change the order of 3 and 1 again. 3, 1, 2. But here you can get from here to here, but again exchanging 2 and 3, right? So you get this, and here you can get here from here, but exchanging the 2 and 1. So you can also get here, right? And here in the top you'll have 3, 2, 1. So that's the order for the symmetric group of 3 elements. Yeah, and of course you need that's only elementary only elementary errors, and of course you have these and these and most of all this. Okay, so that's not very hard, in fact, if you know that Brouwer cells of the inside SON, there are Brouwer cells probably even better to speak about SLN. There are Brouwer cells, right? And that these Brouwer cells actually intersect if and only if and dual Brouwer cells. And dual Brouwer cells. And these cells are, determined by permutations, and in the Brouwer, and they are invariant of the Toda system. They are invariant manifolds, invariant varieties of Toda system, and then you just need to know that they intersect if and only if the corresponding permutations are comparable with respect to Brouwer order. So this is not very hard, and the hardest thing here was to prove that Brouwer cells were invariant manifolds, invariant varieties of the Toda system. We did this by choosing certain invariant family of functions of Brouwer system. But then Volodya explained me that the invariance of Brouwer cells has been known before us in more general situations. Actually, that's number 3 of my talk. It was the second result. The first result was about the interpretation of chopping procedure as a procedure of the argument shift procedure in some sense, which I haven't seen before. It's very simple, but I think it's worth mentioning. The second was this.
Just one question, but besides these trajectories, they exist the ones that do not connect permutation point.
Yeah. There are no every trajectory goes from one permutation to another. Every trajectory. There are no others. But sometimes they go from the lowest. Most of trajectories go from the lowest point to the highest point. Measure 0 trajectories go between some other points. Most trajectories with probability 1, if you choose if you use some
As far as I remember, these Brouwer cells and dual Brouwer cells, they exist explicitly the leaves of dressing transformation.
I actually doubt this a little bit. I doubt this, and the reason is that there are different versions of Brouwer cells, double Brouwer cells. Different. For instance,
So
for us, Brouwer cells are B plus, W, B plus.
Yes.
And dual Brouwer cell for us, B minus, W, B plus. And in most papers which deal with Brouwer cells and dual Brouwer cells, people use B minus, W, B minus. But for us, it is B minus, W, B plus. They're different. So, although I also agree that there should be something like that, but I really doubt it is possible to.
There are quartic of dressing, you see, this G plus G minus and action, dressing action. I mean, G plus and G minus, it's a decomposition
Maybe.
of dual Poisson Lie groups.
Yeah, I understand that there are dual Poisson Lie groups. And also would love to have interpretations of our results of our vector fields. I'm going to speak about vector fields pretty soon. I would love to have the interpretation of our vector fields in terms of dressing fields. But so far I couldn't find, well, I'd really love to discuss this with you. Probably you're probably the best person in this direction, but I couldn't find the appropriate citation, the appropriate citation, the appropriate quote, appropriate reference. There's always something a little bit off, just a little bit, like this plus and minus here. Just very little. By the way, B plus, B minus, W, B plus appear in some old papers of algebraic geometers, Deodar and others, where they use the decomposition in the study of combinatoric properties of flag spaces, of Schubert decomposition and so on. Yeah, but when I look through the papers of people in cluster algebras, they always spoke about B plus, B minus, B minus. Maybe I just was not attentive enough. Okay. Well, okay, let me say a few words about generalizations. So, as I told you, this system appears
Georgy,
from...
may I ask you?
Yeah, sure.
So Borja Kruglikov here. So this on the right hand side, what you draw is also known as Hasse diagram, right? And
Yeah, sure.
it's used to compute cohomology, right?
Sure.
On the other hand, you have this flow. So is it kind of that's gradient flow, right? You're talking about.
Yes.
Is this function which is gradient of is Morse function?
Sure. It is Morse.
Yes. So it gives complete correspondence for computing cohomology. Yes.
Yes, it is Morse function, and people used it to compute some cohomology. I think in this case it's not very hard, because in this case it is just a flag space, a full flag manifold, and people know its cohomology from some independent constructions. But it is interesting.
But then it can be generalized to other flag manifolds,
yes,
right?
Precisely. In other cases,
yes. Then you can use general Hasse diagrams for Gmod P, where P is everything.
There are a few interesting questions which arise from here. Well, I'm going to speak a little bit about the Weyl groups. I mean, here I began with the Cartan decomposition of SLN as a direct sum of SON plus symmetric matrices, right? But it turns out that all real semi-simple, all real forms of semi-simple Lie algebras have this kind of Cartan decomposition. So let G be a real form of a semi-simple Lie algebra. And then we have the Cartan decomposition in the direct sum of maximal compact subgroup and some, well, subspace P. We can assume that this subspace P actually contains the Cartan subalgebra. It's not always the case, but in most situations it is the case. It is called the split and non-split case. So let's assume that Cartan subalgebra is completely inside P. Then we have the decomposition into...
well, you always have reduced Cartan subalgebra in P, right?
Yes, yeah, but we didn't do much in the generic case. In the generic case, when you have non-split, you can have multidimensional root subspaces, which are not of dimension 1. And for our purposes, it is important to have one-dimensional root subspaces. We always assume this for the sake of simplicity. Maybe you can do this in general case as well, but we assume that root subspaces were dimension 1, and that for that purpose we actually wanted to have split decomposition, split form. Sorry. So we have direct sum of E alpha minus E minus alpha plus katan plus sum of E alpha plus E minus alpha. So this is P. And then the projection from P. So then we have a projection M from P onto K, which actually deletes the katan part from our notation. And changes the sign of the minus part. So this gives us a possibility to consider the generalized full symmetric Toda on the space P, of which I sometimes call space of generalized symmetric matrices. And it is written down in the precisely same way. L dot is equal to M of L commuted with L. So this system has also been studied. It's also known that it is governed by a vector field T lambda, where lambda is a katan element, on the maximal compact subgroup, right, in precisely the same way. And that this field is also gradient, it's also known. However, in this case, however hard we tried to find, so we also know that Bra cells are invariant here. They're also invariants of this vector field. So it was almost evident that we wanted to prove that the same fact about Bra order is true for general case. However, in this situation, we couldn't prove this by straightforward, by just citing some work, because in this case, we had to work with real Bra cells. And all available literature only dealt with complex Bra cells. Whenever we found a paper which would deal with the properties of Bra cells, it all began with the phrase, let G be an algebraic group over characteristic 0 algebraically closed field. And that always was the first phrase. So we tried our hard to find the reference. We asked people in the field, but nobody knew what to say. So we somehow modified the proof. And it turns out that one can derive this property straightforwardly from the properties which are known. From the fact that this function, this vector field is gradient, also from the description of its stable points, which are also given by elements of the Weil group now. From the description of the values of this function, of the gradient of the Morse function, which we spoke about in these points, and from the fact that when you have a trajectory which enters some point, and there is only one point beneath it, then this trajectory entering this point should come from the point in the below. So you can now reverse the reasoning and prove the properties of Bra cells, of real Bra cells, using the properties of complex Bra cells, which somehow restrict the properties of real Bra cells, and the properties of the integrable system which exists there, which is quite interesting in my opinion. Okay, that was the third fact. Now I'm going to speak a little bit about the symmetries and about this new result, which is not even yet published. So I'm going to speak about the symmetries of the full symmetric Toda. To this end, I recall you the definition of the Toda field. So I'm going to speak about the symmetries of full symmetric Toda system in terms of the symmetries of Toda field, which is the same for me. Yeah. So T lambda is minus or plus, I don't remember. To this end, it doesn't matter much. So here lambda is a diagonal matrix. With certain spectrum. Well, first of all, it is easy to show that T lambda 1 always commutes with T lambda 2. It is analogous to the fact that the integrals trace L to the power k Poisson commute with each other, equivalent to this fact. Let me sketch the proof. The proof is pretty simple, but it relies on two formulas which I couldn't find in the literature, so I had to prove it. It was easier for me to prove it than to find it in the literature, although I'm almost sure they should have appeared somewhere. Well, actually, the first one, yeah, the first formula appeared in the literature, that's true. I even found it. And the second is, so the first formula is the following. If you take M, and you consider it as a projection from symmetric onto SON, and you have the following equation. M xy, which is actually just xy, of course, minus M mx y minus M x and y plus mx and y equal to 0. Yeah, 9 Hertz, precisely. Actually, 9 Hertz should have square here, but since it's projector, we don't need this square. So that's the 9 Hertz, and it turns out that it's known for this M. But if you to this end, you need to interpret M as a projection onto SON from SLN along B minus, right? If you take this projector, then it is easy to see that when you restrict these to symmetric matrices, that's precisely the math M you need. Just the projector, nothing else. Nice. But so when you have this projector from Lie algebra into a Lie algebra along another Lie algebra, this projector always verifies this equation. It's easy to see this. It's Volodya said that it's been known by Kosman Spatzbach, and it was found discovered. So it's, yeah, I rediscovered this somehow. Okay. Now further, the second formula is the following. Let X and Y be two vector fields on a Lie group. We can always write down a vector field on a Lie group as in the form of some vector valued function, the algebra valued function on Lie group, which you which you move to the point G by right translations. And the same for Y. Every vector field can be written in this form, where x, small x, and small y are maps from G to Lie algebra of G, nothing else. Then you can write down the commutator of x and y as Z of G multiplied by G, and Z of G can be written as follows. You take the derivative of the vector valued function y along the vector field x. Subtract the derivative of x along y and subtract the commutator of x and y in the sense of Lie algebra. A very simple formula which I couldn't find in the literature. Very simple. So now you take two vector fields of this form. Use this formula. Apply this formula. Then you obtain precisely the right-hand side of this equation. And you obtain precisely this right-hand side of this equation. So you replace this with the left side. And what you have here will be equal to m of the following combination: psi lambda 1 psi transposed, psi lambda 2 psi transposed, which of course is equal to 0 because lambda 1 can mix with lambda 2. So that's how you prove it geometrically, so to say, not algebraically. And then the idea was to generalize this a little bit further. So let us take arbitrary matrix X in SLN. And then you can ask, what will be the commutator of two such vector fields, Tx and Ty? And precisely in the same manner, is in the same formulas. You can show that it is equal to T of the commutator, X and Y. So Volodya said that it probably is Dressen transformation, Dressen vector fields. Maybe. I couldn't yet find this. Couldn't yet. But what it is interesting that we have now a representation of the Lie algebra SLN by vector fields on SON, on the Lie group SON. And so the dimension is twice as large, as big as the dimension of SON, at least twice, even more than that. So of course, these vector fields cannot be linearly independent everywhere. And these vector fields are not, of course, are not invariant with respect, and are not symmetries of Toda fields. For instance, if you take X equal to the matrix, unit matrix Eij, and you commute Tx with T lambda, and up to the sign, what you get is lambda I minus lambda j times T lambda by this formula. So it's not invariant. However, if you multiply this Tx, Teij, by very simple function, so I think I don't have time to explain how you can actually get such functions from some general principle, but here you can just take the lower the elements from the lower row of the matrix psi and take their ratio and multiply it by Eij. And this already will be, of course, a symmetry, because what we get from this commutator will be cancelled out when you act T lambda on this function. So it's 0. It's symmetry. Let us denote this vector field Tij. And now you can prove.
But it depends also on n.
What do you mean n? N is the last row, so
Yes.
so it's actually somehow n is fixed.
Okay.
Somehow it's fixed. It's all the same for all elements of this side. So it is remarkable that Tij, they give you a Lie algebra of vector fields. It's a Lie subalgebra, finite dimensional Lie subalgebra, because you have the following commutation relation. Quite interesting. Well, I hope I will not mix the signs. It's something like delta Pj Tiq minus Tpq minus delta Iu Tpj minus Tij minus delta Jq T, I think Ij minus Pq. I'm not sure about all the signs, but I think it is
P or PI?
Pj. Yeah, it's just like in the GLN, just like in GLN. But here you have some extra terms, and I think it is some kind of deformation of GLN. It's like some algebra. Actually, I think we discussed this with Dima, and Dima observed that it is some subalgebra in GLN. And now it is just a matter of some technique to find a resolvable subalgebra inside this Lie algebra. For instance, I think there are plenty of them, but what I found was something like this. You take, so first of all, you observe that
Maybe it would be nice to make to regroup it.
yeah, sure. Actually,
And
I tried.
Then it will be clear that it should be some deformation of GLN. If you regroup it, you will
It's
see.
actually, I think it's what Dima observed, that if you take elements of the form Eij minus I think Ei or Ejj, I don't remember. Either this to be Tij. Then what you get will be, within the commutation relations will be the same, except that here Tii are equal to 0, and we need to add them. They are central. It's easy to see that these elements are central. So now, okay, so now it is easy to choose the resolvable subalgebra, but I did it a little bit in a little different way. I wrote down this as I took the upper triangular part of this, and then in every column I took the difference between the last non-trivial, non-central element in this column and all the others. So every column will give us n minus, so kth column will give us k minus 2, I think, elements like this. K minus 2 elements. So and it is easy to see that elements of the form Tij minus T J, I think, so I is the number of row and J is the number of column, right? So it is J minus 1J. So if you so you note this by some tau Ij, and then elements in the same column will commute. Tau Ij commute with tau Kj for all I and K, right? And if you take elements from different rows, you will always end up in the next in the higher row. Always end up in the higher row. Tau I j tau pq will belong to linear combination of tau. So q, let q be greater than j of t sq as from 1 to k minus q minus 2, something like that. Yeah, so it's resolvable.
And the last one will be commuted.
Yeah, so the last one is commuted because it's just the column.
Number of elements.
And the number of elements is equal to n minus 2, n minus 1 divided by 2. But then you add all the diagonal elements, which is still there, plus n minus 1. And that gives you precisely n minus 1, n divided by 2. So that's as many as you need. So that's interesting. Never seen this in the literature. I hope I haven't made mistakes in the computations. I haven't yet published this, so we plan to do this.
Beautiful.
Yeah, it's very nice.
Okay, give me for a moment.
Mhm.
Thanks a lot. Questions and remarks?
Georgy, if you have this Lebesgue integrability, then you have a lot of integrals, right? So which probably means that your Hamiltonian system,
First integrals, yeah, we have lots of first integrals. That's true.
which means that your Hamiltonian system is resonant, right?
Is super integrable. It is known
Super
that it's
integrable. But then in particular, that like this lower, super integrable. So lower dimensional Tori.
yeah. It has. It's been known that it's super integrable. I think Yuri Chernikov and Alexander Sorin, they proved this. Also, there is a different proof given by Nikolai Reshetikhin and Schrader, Gerhard, I forgot the name of this young. Gerhard? Gus. Gus Schrader. Gus Schrader. But I still don't know if the system which Reshetikhin and Schrader considered was the same. Their system lives on the symmetric space G quotient by the maximal compact subgroup. This space is known to be Euclidean, to be isomorphic to Euclidean space. By the
It's Gilfand pair.
I don't know if it's Gilfand. When you quotient
Group and
Yeah.
you have a compact subgroup
yeah,
in such a way that the quotient is a symmetric space.
I think it's always if you take a semi-simple group and you quotient out the maximal compact. I didn't know this.
That's non-compact symmetric space. Yes, it's diffeomorphic, right?
It's diffeomorphic to some Euclidean. It's locally compact. It's diffeomorphic to Euclidean, but the diffeomorphism is somewhat of a mysterious nature, I would say. It's given by very I know how to prove this. It's proved by considering the sectional
No, it comes
curvature.
from Iwasawa. This diffeomorphism comes from Iwasawa.
Yeah. I think Iwasawa actually comes from this, more or less. But Iwasawa it's also mysterious, in my opinion. I mean, you can all the decompositions of groups in the products of subgroups. You can prove it, but if you try to write down the explicit formulas, you're always at a loss. I think it's just it's like the problem of finding of diagonalizing a symmetric matrix. In theory, you can always do this. But if you try to use this, general construction to write down certain functions, you get something, barely manageable. Let's say.
When you have a Iwasawa decomposition, you have another homogeneous space. You have Hermitian symmetric space.
Yeah, lots of, I think in this case, it's not Iwasawa, it's more.
No, I mean, in the case of Iwasawa, you have a Hermitian symmetric
what I spoke about is I think I remember actually last year I refreshed this from Helgason's book, and I think in Helgason's it's proved by first introducing certain Riemannian metric and then checking that this Riemannian metric, when you pass it to the quotient space, gives you sectional the metric with negative sectional curvature, and that actually is the key to this fact. Then you just use this fact, and that's enough. I think that's how it was proved, but I don't remember. In any case, the details are always quite horrific, if not horrible. Yeah, it's very, very, very indirect, as far as I can remember.
No, Iwasawa it's refining of Cartan decomposition, which you already used.
Sure.
So another question is that's this Morse function which we were talking about before. Is it just like square norm with respect to this B form, which is related to Killing form through involution?
It's a little bit more complicated. First of all, it's actually quadratic. You are right. It's quadratic. It's quadratic. It's something like. Let me see. It looks like in this case. Let me recall it. It's something like you take trace of the product of certain matrix n with L squared, I think. Eventually write it down in terms of double commutator, but this matrix n is pretty natural. It's diagonal, which looks like 1, 2, and so on, n on the diagonal.
That's involution. L go to an L, that's involution. Grading reverse involution. So from Killing form, you will get another form which is.
But then after you've chosen this this function, you also need to modify the Riemannian structure as well. Riemannian structure is not also the one given by Killing form. You need to modify this form by dividing certain coefficients. After you have divided certain coefficients, you can actually expand it to an invariant Riemannian structure on the group, on a compact group, and that's how you get the gradient function. It's actually interesting. I thought a lot about this because when the same system is at the same time Hamiltonian and gradient, I would expect that it should come from some complex system, which is when you have complex system, complex Hamilton function, you can always take its real part and complex part, and real part will give you gradient, and complex part will give you Hamilton, as far as I can remember. That's a general principle, but in this situation, I couldn't find any reasonable reference, any reasonable paper where such a thing has been discussed, would be discussed. I don't know. It's a very natural question. Yeah, but not at all known. The answer is not known as far as I can remember. No. Maybe you can actually do without this modification of the Killing form by modifying the function, but we couldn't find a way to do this. It's an interesting question. What is also interesting is that this function is always a Morse function, even when with a little bit modification. When lambda has simple spectrum, it's Morse on the nose. It's just the usual Morse function. But when lambda has multiple eigenvalues inside, then you get a more Smale function. Yeah. And in that case, you need to modify the description of the Toda flows. They will be governed by some modification of Brouillard order on permutations with repetitions. That's another thing interesting, but quite complicated in the world of combinatorics. Yeah. So there are lots of questions. For instance, I've always been wondering if you can reinterpret this Hasse diagram of Brouillard order as some kind of discrete integrable system. That would make sense because this Hasse diagram is a, is the phase portrait of an integrable system. So it might be some discrete version of integrable system itself. But I don't know.
I don't know what you mean. It's finite number of nodes, and flow goes in the same direction.
Yes,
so
yes, but I mean, yeah, you're right. But you can work with, you can actually consider this diagram as a quiver, and then on quiver you have integrable system representation species of quivers. You have an integrable system. So there are lots of ways to work in this direction. And also, if you know, then maybe you can answer the question: what happens to Brouillard order, to Hasse diagram of Brouillard order when n goes to infinity? What is the Brouillard order? What is the Hasse diagram of Brouillard order for S infinity, for infinite symmetric group? Don't know it.
Okay, more questions.
Sorry for. I think I asked
Well,
more questions
thanks a
than
lot.
I think I asked more questions than the audience.
Just a comment. I think they're stabilized Hasse diagrams because they're actually going to compute the cohomology of like semi-infinite Grassmannians and similar flag manifolds.
It should be.
Yeah, it should
They
be literature.
Yeah, they actually do stabilize somehow. That's true. There, where you can always find this Hasse subdiagram inside Hasse diagram of higher dimension, and that is very interesting because it is known that when you take the original open Toda chain and let the number of nodes go to infinity, that as the limit, is what they call in a Zemtsev limit, I think, you get the wave equation. So what kind of equation you get in this case when the dimension of symmetric matrices goes to infinity? What would be? I don't know. It's a very interesting question, but I don't know how to answer it at all. Okay, sorry for.
Okay, thanks a lot. It was very
off
interesting
topic.
and beautiful. So, I hope this is not the last talk by you. I also hope so. So, we'll meet next Wednesday.
We still speak English.
Hmm?
We still speak English.
Until we
Close
close
Because I
the.
didn't ask the.
Okay, goodbye. Thank you.